All right, let's look at number one. What average, mean, median, or mode is associated with the standard deviation? The mean. The mean is because when we calculated, recall we did the calculations by hand. We are calculating the basically how much it varies from the mean. We're using the mean within our calculations. Okay. Two, what is the relationship between the variance and the standard deviation of a data set? So, what is the relationship? Okay, I can find my notes if I need to. Basically, we talked about, let me go to minimize. You've got the variance is s squared and the standard deviation is s. So basically, what it is the standard deviation is the square root of the variance. It's the square root because I just take the square root of what the variance is. So the square root of the variance. Okay. All right. I submit my first answer. I did submit. Okay. Oh, I didn't submit my first answer. I don't know if it's right or not. Okay. Yes. Okay. I don't know. It's work now. It's kind of confusing. What symbol is used for the samples or the standard deviation when it's a sample statistic? What's used for it when it's a population parameter? So when it's a sample statistic, what are we using for the? It looks like we're asking for the standard deviation. So the standard deviation when it's a sample statistic, we call it's S. But when it's a population parameter, it was sigma. Oh, I didn't. That's poor formatting there on my part. That should be a sigma. That I did not use the right Greek letter there. I could never make it in a frat. Dang it. So that was I don't know. That was a formatting error. It's supposed to be sigma, but four. Now we're going to get to use our BFF salt. Consider the problem. We explore the effect on the standard deviation by adding the same constant to each data value. So we've got a data set. So first thing I'm going to do is use salt. Now, defining formula, as I said, I really don't. You can use the defining formula. The defining formula was this right here, but I'm good with y'all using technology here because that takes too much time. So what I would do instead of using the defining formulas, I'll go to descriptive statistics, and I'm looking for or the computation formula or a calculator. Oh, they said or a calculator. Maybe I should read the whole question. Or SALT to compute S. Now S is this sample standard deviation, and that's going to be the default standard deviation that SALT's going to give you. There is a population standard deviation. It's not given to you. They give you the default. So I can just do Control C and then Control V. Okay. Now add 3 to each data value. Add 3 to each data value for me. Now, you might have a different one. So I'm going to go to data set. I'm going to edit these and I'm going to add 3 to each one. So add 3. Add 3. Careful. Oh, my backspace wasn't pushing the right buttons there. Be careful to do yours. And you could also do this in the calculator using list. Okay, 17. So I add 3 to each one. So 17, 15, 9, 17, 19. Okay, 17, 15, 9, 17, 19. And then what I can do is I can go back to descriptive statistics now, and it will update my new standard deviation. So Control C, Control V. Uh-oh. What are we noticing here? They're the same. Okay, so there's a kind of a thing that we got to talk about. Adding the same constant to the standard deviation results in it staying the same. Standard deviation, here's why. Standard deviation is a measure of spread. It's a measure of how spread out a distribution is. So if I'm adding 3 to values, if I had, let's say I had a test and the lowest grade was a 60 and the highest grade was 100, and the lowest grade was a 60, the highest grade was a 90, and I had 10 to each score, so somebody could get 100. So if I go from 60 to 90, what's my spread? 30. If I add 10 to each score, what's my new spread going to be from 70 to 100? 30. So you see, my spread does not change whenever I add a constant. So that's a thing. Now, like the mean, obviously, like the average test score would change, and maybe the mean, median, and mode would change, but measures of spread do not change. There's a few more measures of spread we got to talk about as well on the next lesson. And this problem will explore the effect by multiplying each data value by the same constant. So now we're going to look at multiplying it. And this is kind of an extension of the notes. Like, this is a good thing I know and cover a lot deeper. So I've got my 5 values. It says either one you want to do. So you want to do it by hand or you want to use calculator or salt. All I got to do is go over here, select that, Control C. And I better pay attention too. I didn't do a good job last time of paying attention to decimal places. It was 4 decimal places. I got lucky there because I wasn't even paying attention to that. So it's just 4 decimal places. So make sure you're not like me. Multiply each data by 3 to attain the new data set. So multiply each one by 3. So I could go back here and multiply each one by 3. So 14 times. So you could do 14 times 3, 42. But you could, so 42. 10 times 3 is 30. 9 times 3 is 27. 13 times 3, 39. And then 15 times 3 is 45. So that's your new data set. All right, and then we'll go now look at the descriptive statistics. And we'll look at our new standard deviation. Control C, Control V. Okay. So let's analyze this a little bit. How would we say the new standard deviation was impacted by the old one whenever we multiplied everything by 3? So multiplying by the same constant results in the standard deviation being, see, this is 3 times as large as that. So it would be absolute value of C times as large. Okay. All right. It's just like if I had a 50-point test and like student A got 45, or the highest got a 45, the lowest got a 20. If I multiply them by 2 to make a 100-point test, then it's 90 to 40. So now the spread becomes twice as big in the scores. You record the weekly distances you bicycled in miles and compute the standard deviation to be S equals 2.3. Your friend wants to know the standard deviation in kilometers. Do you need to redo all the calculations? So we've got to measure a spread for miles, and we got to convert it to kilometers. Do we need to do all the recalculations? Or what could we do? Yeah, exactly. Just multiply it. So when you're making conversions, that's good. You don't have to do all that work again. All you have to do is multiply it by the appropriate one. So we've got 2.3 miles is at 1.6 kilometers, or 1 mile is 1.6 kilometers. So we just got to multiply it by whatever that conversion, that factor would be. So I'm just going to take 2.3, my standard deviation, or whatever your standard deviation is, and multiply it by 1.6 to get that into kilometers. 2 decimal places, so 3.68. Okay. Okay, so we've got a large data set here. Some things I didn't talk about. I didn't talk about the range, but we'll pick that up here. NASA Space Shuttle standards of eProxy were tested at 9% braking strength. The following data is time and failure for random sample of 50 eProxy strands. Let X be the random variable representing time and failure for 9% braking strength. So I'm going to click Use Salt. Okay. Now, range, I don't believe it gives you the range here. Well, it kind of does, because y'all know what is the range of a distribution. I did not cover this very well. Exactly, the maximum value minus the minimum value. So I could go to the data set and kind of track down which one's the highest, which one's the lowest, or I could just come here, 7.89, the max minus the minimum. So 7.87 for me. So 7.87. Now, this sigma of X represents the sum of all the x values. What does that mean? I promise you it's not as complicated as it sounds. What are all these values added together? Now, doing that in your calculator would take a while and wouldn't be much fun, but we've got Salt here to save the day. And so what we can do is we can go over here and click the box sum. We can go click the box sum. And what the sum does is it will do the sum. It will add up all those values for you. So I just go click sum and it spits it out for me. So I Control C, Control V. The sigma x squared means the sum of the squares. The sum of the squares. So the sum of the squares, guess what? I can go click on that right there, sum of the squares. So I can go click on that to add that to my output. Control C, Control V. They didn't say anything about rounding there, so I'm assuming they want the whole thing. Use the results in Part B to compute the sample mean, variance, and standard deviation. Okay. Now, by the way, what they're saying here, they're setting you up. Like these are the values you would use to calculate the sample variance and the standard deviation. But we could also just use our calculator here. The sample mean is X bar. So all that is, I got to go over here. X bar is just the sample mean. So I just got to go to the mean there and Control C. So X bar is just the mean. It's a sample mean. The bar means it's a sample. S squared is the variance. Okay. I don't know if they give you a variance here. Yeah, they don't give you variance there. But what I could do is go grab the standard deviation. Control C. Go grab that standard deviation and put. And so now I'm going to do the standard deviation first. I'm going to grab that standard deviation first. And then I'm going to use that to find the variance. What do I have to do with this value to get to the variance? What do I have to do? Square it. So yeah, so 1.3329 squared. And now I got to go 4 decimal places, 1.7766. All right. All right. Next, what I'm going to do is use results in Part C to compute the coefficient of variation, okay? Now, they are going off, there's 2 coefficient of variation formulas. There's one with a sample values and one with population values. If I'm using Part C, they're giving you a hint. They want you to use this one right here. So how do you find the coefficient of variation? You take your standard deviation. So my standard deviation is 1.3329 divided by the sample mean, 1.2426, and then times that by 100. So take your mean or your standard deviation, so your S, divided by your X bar, and you times it by 100. And they want to the nearest whole number, so 107%. Okay. %. So what does this mean? I briefly went over this. I don't know if I did a great job. If it's over 100%, the key is if over 100%. Like in our notes, it was less than 100%. So that meant when it was less than 100%, that means that the mean was larger than the standard deviation. If it's less than 100%, because this is less than that. If it's over 100%, that means the top's bigger than the bottom. That means the standard deviation is bigger than the mean. So the standard deviation is slightly larger than the average time. Do you see how the standard deviation, 1.3329, is larger than the average time? Okay. So what does a small CV represent? So like in our notes, we had a small CV. That means the data is more consistent because the numerator is smaller. Okay. What that means is basically if the numerator, the smaller the standard deviation, the less spread there is, and the more consistent the data is. It's not all over the place. So this would be kind of I would say this might be a little bit concerning, this 107. That's a large coefficient of variation. Okay. Consider the data set. Now, can we use the defining formula? Yes, but is that what I would do? I wouldn't. So I'm perfectly fine if you don't use the defining formula. You've got salt. You don't have salt there, but we could use our calculator. So there's the defining formula. If you wanted to do that, you could do that. But here's what I'm going to do. I'm going to use my calculator. Now, range, we could spot that. Range is just highest minus lowest. 8 minus 2 is 6. But you're welcome. I'm good with you using your calculator here. Okay. You will not have to know on a test how to do these formulas here. So I would just enter it in the list in the calculator. Now you could also go back to one of these salt things and delete, I guess, like enter it into salt, like enter that data set into salt and like delete the extra ones, but that would be a little bit time consuming. Okay, so stat enter to get to this point. So stat enter. And then I go to stat calc 1 bar stats. And they're wanting the sample standard deviation first, 2 decimal places. The sample standard deviation is S of X, would be 2.41. And then the population standard deviation is next, that's sigma of X, so 2.15. So you could use the formulas. The key is if you do the formulas, on this one, you're dividing by n minus 1. On this one, you're dividing by n. And so this one's going to be less spread, more precise. That's the key on that one. Okay. Eight's a little time consuming as well. So let's talk about that. We've got salt back for us though. The location in Ireland is a place of a great archaeological importance. The region's been occupied for people by more than 4,000 years. They have subsurface anomalies. The magnetic field these surveys have led to many significant archaeological discoveries. After collecting data, the following data to measure magnetic susceptibility on the 2 main grids are shown below. So compute sigma of X. That's just the sum of the X's. I'm going to use salt for that. And now this time you have 2 variables. So we'll make this work. It's not that bad. Salt does a great job with this. So what I can do is go to descriptive statistics. I'm going to click sum. Descriptive statistics, I'm going to click sum. And so they want sigma of X. So that's the sum of X. So that's the sum here. Control C, Control V. Sigma of X squared. What is that? That's the sum of the squares. You got to click on sum of the squares as well. So you got to do this for the X and the Y. So sum of squares is right there. Control C, Control V. Do they say how many decimal places they want? I don't see it. I guess I'm just going to go off of what they're giving me here. Sigma of Y, that just means the sum of the Y's. That means all the Y's added together. So there's your sum of Y's. Control C, Control V, and the sum of the squares. So the sum of the squares of the Y's. So that's going to be the sum of the squares. Control C, Control V. All right. Use the results in part A to find the sample mean, variance, and standard deviation. Now, what they're wanting you to do is they're wanting you to use these formulas here, but we're not going to use those formulas. It's already given to us. So we're just going to go off. We're going to cheat and use the given to us. So we're going to start with X. So X bar is the mean of the X's. So I'm going to put the mean of the X's, Control C, Control V. Whoops, got to fix that formatting issue. Now, remember on this one, they don't give you the variance, but they do give you the standard deviation. So standard deviation, Control C, Control V. They do a good job of telling you whether they want the population or sample standard deviation. So they do a good job to not keep you having to do that. So now this standard deviation squared, the variance, I take 9.7703 squared. It should be 95 point, how many decimal places? 4.4588, 95.4588. Now we're going to do the same thing for Y. Not too bad. So Y, we'll go to the Y mean. Control C, Control V, sample standard deviation, Control C, Control V, and then the variance is just this squared. So 13.9337 squared. 194. Okay. Got a little bit of rounding I got to do here. 194.1480. Okay. Light work. Okay, so the Chebyshev interval, the 75% for the mean x values. You're going to use these values here. So the Chebyshev is, for 75%, is mu minus 2 times standard deviation and mu plus 2 times standard deviation. My mean is 20.3536 minus 2 times the standard deviation, 2 times S. And we're using the S here. We're using the, using S here. All right. So I subtract 2 standard deviations, and then I'm going to add 2 standard deviations. It's going to create an interval. And how many decimal places do we want? 2. So now this one's a little different. So I'm going to put 0.81, and I'm going to put the word 2, 39.89. I almost did the comma thing again. So the Chebyshev's formula is just take the mean and subtract 2 standard deviations, so 2 times standard deviations, and then the mean plus 2 times the standard deviation. Okay. Do the same thing for the y's. So the mean, 28.0933 minus 2 times the standard deviation, 13.9337. And then 28.0993 plus. So 0.2332, 55.96. Okay. Now we're going to see which one has a wider range of values, the first grid or grid H or grid E. So which one's wider? Well, this one down here is a lot wider than that one. So it's going to be the bottom one with the Y's. The Y values are in grid H. So grid H is going to be the larger one, 75% of values, because this is a 75% interval. All right. Now the sample coefficient of variation for X, the sample coefficient of variation, you're going to go back. I'm going to go back up to the X values. The sample coefficient of variation, this formula right here. So it's your S value, 9.7703 divided by the mean, 6 times 100. So 48.0. They want probably nearest percent. Oh, I messed this up, didn't I? They want, so this would be 48%. Sorry about the glare. Oh, decimal place, 48.0. And then the one for the Y. So I got to scroll back up here for the Y. Be careful when you scroll. When I scrolled, I accidentally selected the wrong answer there. So it's going to be the standard deviation, 13.9337 divided by the mean, 28.0933 times 100. 49.6. 49.6. So the coefficient to compare the two grids. So which one has a greater variability? So what you're going to do is you're going to compare which one is greater, the X or the Y. The Y is greater, and the Y represents grid H. So grid H is greater variability per expected signal. Per is a division one, so variability, so like spread, per expected, the mean's the expected value per expected signal. So grid H has got a greater one, greater percentage there. Okay. Let's think about this. If S represents the variability of the signal and X bar, which sample mean represents the expected level of the signal, then the S divided by the X bar can be a measure of variability per unit. Remember, this is a considerable variability. So why in this case would a large be better or at least more exciting? So why would a large be better? So a larger might be a possibility of more varied artifacts, because basically there's more possibilities there because the spread is larger, So the spread's larger. That means the range of values can be larger. So you could have more buried artifacts. Okay. All right. Number 9, I think we're done after number 9 here. It's going to be light work. Okay. Consider the population data. Consider the population data. So it's population sigma mu. Compute the coefficient of variation. So coefficient of variation is sigma divided by the mean times 100.
On the last question, because we're still on it.
So on this one, you're taking the sample standard deviation, or the population standard deviation divided by the mean, and you times it by 100. So that would be 5%. Okay. Compute an 88.9% Chebyshev interval for the population mean. So Chebyshev's interval, so it's right here. 88.9% means we're going to subtract 3 standard deviations and add 3 standard deviations. So it'd be 40 minus 3 times 2 and 40 plus 3 times 2. So it'd be 34 to 46. And they're going to do lower limit to upper limit. So 34 to 46.
Where did you get 30 from?
Okay. The 3 comes from the number of standard deviations it is below and above for 88.9.
Okay, sorry.
So yeah, 75% is 2, 88.9% is 3, and 93.8 is 4.